Hey everybody, so another question I've been getting a lot of is how to tell what the differences are between the delta H or the enthalpy of lattice energy, solvation, solution, and how to tell whether or not they're exothermic or endothermic. So I'm going to go over that really quickly and hopefully tell you all that you need to know about the subject. So in this unit, we're talking specifically about these values in terms of trying to dissolve salts or other types of things going into solution. And if you think about it, those can be divided into two major steps or two major stages. So if you think about trying to dissolve something from a theoretical standpoint, what kinds of IMFs exist in that system when you start off? Well, first you start off with the pure solute and the pure solvent, right? And what kinds of IMFs are there? Well, there's the solute IMFs, right? There's the ionic, bonds between the NaCl's and the NaCl's and all those kinds of things, right? And also between the solvent and solvent, there are also IMFs. So like in the case of water, there's hydrogen bonding and dipole-dipole, and there's kind of waters kind of hanging around and doing their own thing and stuff like that. So the first step when you're trying to dissolve a salt into water is that first you're going to have to break apart these solute-solute IMFs and the solvent-solvent IMFs. That'll be step number one. What's that energy called? Well, like we learned last semester, it's the delta H of the lattice energy. It's the energy that you need to break apart the lattice or the IMFs in the solute-solute IMFs and the solvent-solvent IMFs. So if we think about this all in terms of a graph where this is enthalpy, sorry for the terrifying delta H, and temperature, okay? So let's say that we start off here. In order to first break these IMFs, we have to put in energy, right? Because we're breaking solute-solute IMFs and solvent-solvent IMFs. So we go up and we end up somewhere around there. So that's the first step. The next step, if you think about theoretically how dissolving works, is that once you break these IMFs, you then have to form new IMFs, right? You have to form now solute-solvent IMFs. Otherwise, they wouldn't dissolve and be in solution. So when you reform IMFs, is that an endothermic process or an exothermic process? It's an exothermic process, right? Because you're forming pseudo bonds between two things, and that's going to be more stable, so it's going to be lower in energy. You release that energy, right? So you end up lowering the energy and ending up somewhere around there, okay? So this is going to be the delta H of the lattice energy. And because we're breaking IMFs, it is always going to be endothermic. Or this one right here, this is the delta H of solvation, right? You are solvating, you are actively dissolving the solute into the solvent, all right? So, and this whole net thing, from here to here is the delta H of the solution, okay? So in this case, it would be endothermic. Now we can change these values, right? We can make this one bigger or smaller, or this one bigger or smaller, right? So we could end up where we start off here and we actually end up down there, right? That would look something like that, right? So now our delta H of solution is exothermic, right? Because now it's below the 0 point. So delta H of solution is going to be positive or negative, endo or exothermic, depending on what delta H of the lattice energy is, which is always going to be positive because it's going to be endothermic because you have to put in energy to break those IMFs, and delta H of solvation with a V, it's always going to be exothermic or negative because you're reforming IMFs, you're going to be releasing energy, all right? So that hopefully sums up delta H of solution, lattice energy, and solvation. hopefully that helps out, and good luck.